Welcome back, everyone. So we have finished the journey of glucose through the cytosol, and we've seen what happens when the cell is forced to survive without oxygen. But today, we're looking at the true gold standard of metabolism. You see, when oxygen is plentiful and the mitochondria are ready, pyruvate doesn't just become lactate. It becomes the key that unlocks the massive energy potential of the TCA cycle. Today, we're stepping right up to the mitochondrial gateway to explore the aerobic fates of pyruvate. Let's dive in. Okay, here is our roadmap for today's explainer. Section 1 is the mitochondrial gateway. Section 2, door 1, carboxylation. Section 3, door 2, oxidation. Then we'll hit the PDH toolbox, do some exam preps to test your knowledge, and finally end with the point of no return. Let's start with Section 1, the mitochondrial gateway, the aerobic crossroads. You know, when a cell isn't forced into survival mode without oxygen, pyruvate doesn't just reduce to lactate. Instead, it passes right through the mitochondrial membrane for some major energy harvesting. This transition marks a massive shift from the low-yield world of glycolysis straight into the high-yield aerobic powerhouse of the cell. So, when pyruvate stays in this aerobic environment, it faces a brilliant fork in the road. Within the mitochondria, it really has two major paths. It can either go left, carboxylating into oxaloacetate, or it can head right, oxidizing into acetyl-CoA. Let's check out that first path. Section 2, door 1, carboxylation, forming oxaloacetate. Taking that first path, we run into a really crucial term for your exams, anaplerotic. An anaplerotic reaction is basically one that replenishes metabolic intermediates. Think of it as literally refilling the tank of a cycle, like the TCA cycle, ensuring it can keep spinning smoothly when energy demands are super high. Now, this specific reaction is catalyzed by an enzyme called pyruvate carboxylase. And here is a detail you absolutely must remember. It is a biotin-dependent reaction. Biotin, or vitamin B7, acts as a carrier for CO2, allowing the enzyme to add a carbon to our 3-carbon pyruvate to create a 4-carbon oxaloacetate. And this serves two master purposes. First, TCA cycle replenishment. If the cycle is running low, this anaplerotic reaction refills the tank. Second, gluconeogenesis. Oxaloacetate is a key substrate, and it's actually the very first step in the long climb back up to making new glucose. But what about the other path? Section 3, door 2, oxidation, forming acetyl-CoA. So, in the mitochondrial matrix, pyruvate meets this absolutely massive protein machine called the Pyruvate Dehydrogenase or PDH complex. Actually, scratch that. It's not just one enzyme. It's 3 enzymes rolled into one, E1, E2, and E3. This complex pulls off a pretty slick multi-step maneuver. Step 1 is decarboxylation, where it snaps a carbon right off. Step 2 is oxidation, stripping away high-energy electrons. And Step 3 is activation, where it attaches an acetyl group to coenzyme A. If we take a close look at the exact inputs and outputs here, you'll see pyruvate enters, CoA and NAD+ come in, and then acetyl-CoA, NADH, and CO2 all come out. What's wild is that this reaction is highly exergonic. We're talking negative 33.4 kilojoules per mole, and it is completely irreversible. Meaning, once you turn pyruvate into acetyl-CoA, there is absolutely no going back to glucose. Which brings us to Section 4, the PDH toolbox, or as I like to call it, the molecular Swiss Army knife. To pull off this maneuver, the PDH complex needs 5 distinct tools, or cofactors, to work. You've got TPP from vitamin B1, lipoate, FAD from vitamin B2, NAD+ from vitamin B3, and CoA from vitamin B5. If any of these vitamins are missing, especially thiamine for TPP, the gate to the mitochondria literally slams shut, and the cell is forced right back into anaerobic metabolism, even if oxygen is sitting right there. All right, let's see how much of that stuck. Section 5, exam prep. Test yourself. First up, a conceptual question. Why is the pyruvate carboxylase reaction described as anaplerotic? Think back to door 1 and that definition we reviewed. What does that fancy word actually do for the cell? Did you get it right? It's all about keeping the TCA cycle fully stocked and running. If the cycle is starving for intermediates, pyruvate carboxylase steps in to basically refill the tank with oxaloacetate. Okay, here is a recall question for you. What are the 3 distinct chemical events that occur during the conversion of pyruvate to acetyl-CoA? This is testing your memory of that three-step maneuver the massive PDH complex performs at door 2. The answer is decarboxylation, oxidation, and activation. Remember the simple breakdown? It snaps off a carbon, it strips off electrons to make NADH, and it attaches what's left to CoA to activate it. Next question. Which gas is released as a byproduct of the PDH reaction? Picture the chemical mechanism we studied with the inputs and outputs. What gets snapped off and just floats away? Yep, carbon dioxide. And this is so cool because it brilliantly illustrates exactly why you breathe out CO2 every single day. It is happening right down here at this specific metabolic gateway. Last recall question. Name the 5 cofactors required for the PDH complex to function. Unpack that molecular Swiss Army knife in your mind. Can you name all 5? And maybe even the vitamins they come from? Here they are. TPP from B1, lipoate, FAD from B2, NAD plus from B3, and CoA from B5. You absolutely need to lock these into your memory for exam day. Without them, oxidative metabolism just halts entirely. Finally, let's bring it all together. Section 6, the point of no return, the ultimate commitment. To wrap up today's explainer, remember that pyruvate in the mitochondria is at a massive crossroads. On one hand, it can be carboxylated to oxaloacetate via a biotin-dependent reaction to either refill the TCA cycle or kickstart gluconeogenesis, or on the other hand, it can be decapped and oxidized by the PDH complex to become acetyl-CoA, harvesting NADH and releasing CO2 in the process. But here is the kicker. That oxidation to acetyl-CoA is a one-way street. The cell commits completely. So I'll leave you with this final clinical thought to ponder. Since the conversion to acetyl-CoA is strictly irreversible, how does this one-way gate permanently dictate how our bodies balance burning sugar versus storing it? And hey, all right, let's jump right into this explainer. Today, we're mapping out our cellular energy highways to explore the absolutely fascinating world of human metabolism. We're looking specifically at how our bodies handle glucose, and not just in this very second, We want to see how these systems adapt and literally rewire themselves over the long haul. Seriously, imagine your body's metabolism as a bustling city grid. You've got cars or molecules zooming down all these different roads. We need to uncover exactly how the city manages this crazy traffic minute to minute to prevent gridlock. But we also need to see how it plans for the long-term future when the population, which in our case is our dietary intake, actually changes. It's an incredibly elegant system of microscopic traffic control. To make sense of all this, here is our agenda. We're covering 1. The glycolysis pathway basics, 2. The 3 major checkpoints, 3. Short-term metabolic regulation, 4. Long-term hormonal control, and finally 5. The global metabolic map. Let's get to it. Starting with Section 1, the glycolysis pathway basics. Fundamentally, glycolysis converts glucose to pyruvate in 2 really distinct phases. Think of the first phase as your classic energy investment phase. You know the saying, you have to spend money to make money, right? Well, the cell actually has to spend ATP just to get things started. Then, that's followed by a splitting or cleavage phase that finally pays out ATP, giving us a net energy gain. Now, the absolutely crucial point here isn't to just blindly memorize the 10 independent reactions of this pathway. What you really want to take away is the overall structured journey. We start with a single 6-carbon glucose molecule. We lock it inside the cell by phosphorylating it, invest a bit of energy, literally cleave it right in half, and then journey all the way down to 2 molecules of pyruvate. And along the way, we're extracting ATP through a direct chemical transfer called substrate-level phosphorylation. Moving on to Section 2, the 3 major checkpoints. Like any efficient highway system, we need traffic control. And this pathway has 3 major, completely irreversible checkpoints. These specific regulatory enzymes, hexokinase or glucokinase at the start, PFK1 right in the middle, and pyruvate kinase at the end, they act as strict traffic lights. Because the reactions they catalyze are irreversible, they make sure energy only flows in the right direction based on exactly what the cell needs at that exact moment. Cell has plenty of energy, boom, lights turn red. Starving for energy, the lights turn green. But the ultimate master controller of this whole grid, that would be phosphofructokinase 1, or PFK1 for short. It's the rate-limiting step. Once a molecule makes it past this specific enzyme, it is fully committed to the glycolytic pathway. There is no turning back. It's literally the point of no return for that glucose molecule's journey. Okay, section 3, short-term metabolic regulation. So, to really grasp metabolic control, we have to clearly contrast short-term with long-term regulation. Short-term control? That's your immediate chemical changes, allosteric and covalent modifications, reacting to energy levels in mere minutes. Think of allosteric control like a traffic cop, dynamically waving their arms to direct flow, while covalent control is more like throwing up a temporary roadblock. Long-term hormonal control, on the other hand, takes hours or even days. Why? Because it involves physically building brand new enzymes. It's essentially adding new lanes to the highway. When we look at these rapid, short-term signals, intracellular energy levels really dictate everything. Take PFK1 and pyruvate kinase, for example. If there's abundant ATP, it acts as a massive stop sign, an allosteric inhibitor. The cell is basically shouting, hey, we have enough energy, stop breaking down glucose. On the flip side, high AMP acts as a green light. High AMP means ATP is depleted, which signals the cell to urgently ramp up glycolysis to make more energy. It's just a beautifully designed feedback loop. Let's put this into a scenario. Say your blood glucose is low because you're fasting. The hormone glucagon is released. This kicks off a chemical domino effect using messengers like CMP that physically slaps a phosphate group onto pyruvate kinase in the liver. This phosphorylation completely shuts down pyruvate kinase. It halts glycolysis at the very last step. Now, why does this matter? Well, the liver is essentially turning off its own glucose usage so it can save that precious glucose for the rest of your body, and most importantly, your brain. Which brings us to section 4, long-term hormonal control. Now, what happens when we shift from those quick traffic lights to long-term city planning? Over the long term, hormones like insulin and glucagon don't just, tweak the enzymes that are already there. They actually go right into the cell's nucleus and alter gene transcription. They are drastically changing the physical amount of these regulatory enzymes being manufactured. We are talking about massive 10 to 20-fold increases in enzyme synthesis over hours or days. Let's see how this physical expansion actually plays out with your diet. If you're consistently eating carbohydrate-rich meals, you're in a well-fed state. In this scenario, insulin is the city planner. It signals the cell to literally build more glucokinase, more PFK1, and more pyruvate kinase. You are permanently widening your glycolytic highway to handle all that extra fuel. Conversely, if you're fasting for an extended period, glucagon decreases the synthesis of those enzymes, effectively shrinking the highway back down. Finally, section 5, the global metabolic map. Zooming all the way out to the global metabolic map, we can finally integrate everything we've talked about. You can trace precisely how the well-fed state, driven by insulin, and the fasting state, driven by glucagon, directly govern the entire glycolytic pathway from the top down. They're pulling the strings on those specific enzyme traffic lights we looked at earlier. And remember, glycolysis totally doesn't exist in a vacuum. It is a massive central hub. Sure, it breaks down glucose for energy, but the intermediates created along the way, they serve as absolutely vital off-ramps. For instance, intermediates like DHAP provide the literal building blocks for lipid synthesis, making fats. Pyruvate can be used to synthesize the amino acid alanine. The pathway isn't just a straight line to energy, it's actively providing structural materials for your entire cellular ecosystem. I want to leave you with a somewhat provocative thought. We've just seen that insulin acts as a city planner, right? Literally building more enzymes to permanently widen the glycolysis highway when carbohydrates are around. Knowing this, how might our modern environment, where constantly high sugar diets keep insulin elevated practically around the clock, be interacting with this incredibly ancient, highly regulated metabolic programming? Are we structurally rewiring our global metabolic map in ways it was just never designed for? It's something deeply worth considering as you think about how your daily habits translate into microscopic, long-term blueprints. Hi, everyone. Well, we finally made it. We have reached the absolute final destination of our glycolysis series. Think about it. We have seen every single reaction, counted every ATP molecule gained, and looked at the sheer clinical disasters that happen when things go wrong. But today we're bringing it all together. We're going to look at how your body makes permanent, long-term changes to your metabolism based entirely on your diet, and we'll use a global map to visualize how every single concept we've learned fits into one beautiful integrated system. This is the big picture, folks. Let's wrap it up. Just to give you a quick roadmap of our agenda for today, we're kicking off with the big picture finale, then moving into short versus long-term regulation, navigating the global map, a quick clinical case on PK deficiency, and finally, acing your exam. All right, let's jump right into section 1, the big picture finale. So today, we're bringing everything together to explore how your lifestyle choices, like, say, consistently eating a high-carbohydrate diet, actually trigger permanent modifications to your metabolic pathways. We aren't just talking about slightly adjusting a machine here. We are talking about your body structurally adapting by building more machines, all based on the fuel you're providing it.
Which leads us perfectly into section 2, short versus long-term regulation.
Now, throughout this explainer series, we've talked extensively about flipping switches, right? Things like allosteric regulation, where ATP inhibits PFK1, and covalent regulation, like glucagon phosphorylating pyruvate kinase. Those are short-term mechanisms. They happen fast, in minutes or hours. Think of short-term regulation like a volume knob on your radio that you can just instantly adjust to match the song. It's like changing the speed of a car that's already built. But long-term regulation, that's totally different. That is literally like buying a bigger speaker. You know, it takes days to order it, bring it home, and set it up, but once it's finally there, your total metabolic capacity is massively increased. So the crucial point is exactly how this happens, and it comes down to gene induction. When your insulin levels stay high for several days, it triggers actual gene transcription. Your liver cells get the memo to synthesize brand new molecules from scratch. The result? Your liver can increase its total enzyme count by a staggering 10 to 20-fold. I mean, that is a massive structural upgrade to your cellular machinery. And this massive scale-up doesn't just happen randomly. It specifically targets our 3 irreversible gatekeeper enzymes: glucokinase, PFK1, and pyruvate kinase. This is exactly why a person who consistently eats a high-carb diet is metabolically primed to handle sugar incredibly efficiently. Sure, it takes hours or even days for these new enzymes to be built, but once they are there, the conversion of glucose to pyruvate happens at an enormous scale. That's the absolute hallmark of the absorptive state.
Okay, let's move right into section 3, navigating the global map.
So glycolysis happens in all tissues, specifically in the cytosol, and it always produces ATP and NADH. But from there, we hit a really critical fork in the road, all based on oxygen. Aerobic metabolism requires oxygen and mitochondria, turning that pyruvate into acetyl-CoA to fuel the TCA cycle. On the flip side, anaerobic metabolism doesn't need oxygen at all. That takes place in red blood cells and exercising muscle, resulting in lactate. Oh, and definitely don't forget our fermentation branch for yeast, which produces ethanol and CO2. Now, think about the well-fed state. High blood glucose and insulin basically act as a massive green light. This hormonal state triggers protein phosphatase activity, which totally turns on our regulated enzymes. It causes a drop in glucagon and a spike in insulin, which subsequently increases hepatic fructose 2,6-bisphosphate. And that right there is the ultimate intracellular signal pushing glycolysis forward full throttle.
Conversely, in the fasting state, high glucagon acts as a blaring red light. It binds to cell receptors, triggering an increase in intracellular CAMP, which in turn creates active protein kinase A. This kinase goes straight for hepatic pyruvate kinase, phosphorylating it, and effectively shutting it down. Why? To completely halt liver glycolysis so that precious, life-saving glucose can be spared and sent directly to the brain.
All right, section 4. Let's look at a clinical case, PK deficiency. When we look at patients with rare genetic defects of glycolytic enzymes, the majority actually suffer from a deficiency in pyruvate kinase, or PK. These individuals inherit a mutant enzyme that shows altered kinetics or just decreased stability. And that leads to some seriously devastating consequences for one specific type of cell in particular. And why is it so devastating? Well, because as we know about anaerobic metabolism, red blood cells completely lack mitochondria and oxygen processing capabilities. They rely 100% on glycolysis. So an altered PK enzyme means a total failure to generate ATP. Without that cellular energy, the red blood cells simply cannot maintain its shape or survive, resulting in cell death and severe hemolytic anemia. Which brings us to our final part, section 5, acing your exam. Okay, let's start with a foundational conceptual question. Can you firmly contrast the timeframes and the underlying mechanisms of allosteric regulation versus long-term hormonal induction?
Remember our trusty analogy? Allosteric regulation is instantaneous, happening in minutes to hours. It's the volume knob flipping pre-built biochemical switches.
Hormonal induction, on the other hand, takes hours to days because it involves entirely building new enzyme machines from scratch via gene transcription. It's buying the bigger speaker.
Next question, and heads up, this is a classic board exam trick. Why is the global map so essential for understanding why glucagon inhibits glycolysis in the liver, but totally spares the brain?
Well, glucagon specifically increases CAMP to phosphorylate and inactivate the hepatic isozyme of pyruvate kinase. Basically, the liver deliberately pauses its own glycolysis so that the glucose it has can be pushed out into the systemic circulation. It sacrifices its own sugar consumption to ensure the brain gets the fuel it desperately needs during a fast.
Moving on to a direct recall question, which 3 specific enzymes are upregulated by long-term insulin exposure, and exactly what is the typical fold increase in their synthesis?
A consistent high-carb diet primes the liver by triggering a massive 10 to 20-fold increase in our 3 irreversible gatekeepers: glucokinase, PFK1, and pyruvate kinase.
All right, let's quickly test your signaling pathway memory. Does the fasting state lead to an increase or a decrease in intracellular CAMP levels?
The answer is an absolute increase. Elevated glucagon binds to receptors, generating a massive surge of CMP. This acts as the key to turn on active protein kinase A, effectively initiating the red light cascade that halts energy storage and prompts energy release. I will leave you with this final, real-world application question to ponder based on everything we've covered in this explainer. If a patient on a strict, low-carb keto diet for a month suddenly eats a massive pasta dinner, why might they experience severe temporary hyperglycemia compared to someone who eats carbs every day? Think back to our bigger speaker analogy. Their body just hasn't had the days required to induce gene transcription and build those 10 to 20-fold extra enzymes. Their factory simply isn't equipped for the sudden flood of sugar. It leaves us with a fascinating realization. Your diet doesn't just fuel your body temporarily. It literally rewrites your cellular machinery over time. So I have to ask, how is your current diet programming your metabolic factory right now?
This has been Deep Dive Academy. Learn deep, remember forever.